chapter, the minerals and rocks. And so today, let's move to the structural geology, and which is very important for this discipline, engineering geology, because this lesson relevant knowledge is greatly influence the uh, or stability assessment or risk assessment of rock slope or rock tunnel and some other constructions. So, okay, let's start. So this is the science about the record of rock deformation, faulting and folding. So first of all, I will talk about how we can describe the orientation of rock stratum. So do you remember the disaster map I showed in our previous class? I marked some small symbols like this in a blue color with a long line and a short line, and they are perpendicular to each other. So I will tell you what do these symbols mean. And for example, this is a dipping surface in three-dimension space, and the dip is the angle in degrees below the horizontal, and we usually label the value of this degree just beside the symbol, and the direction of dip is you can see down to the dip, which refers to the short line in this symbol. And strike, this is strike, is direction of horizontal line on the dipping on this dipping surface, and which refers to the long line in symbol in our geological map. And we can use this to express bedding or any geological structures very clearly. And it is used to avoid confusion with ground slope. You see? And this figure is also the one I showed last week for the Shimo landslide, you remember? And for the source area of this landslide, it's a planar surface of rock stratum. And I used another diagram like this to show the bedding surface attitude. So what does it mean? Here I will use play a video for to explain it.
Welcome back, geology fans. Now you're back from your field excursion and are awash in data from your site. It is pretty clear that a field geologist makes a lot of measurements of planar objects and linear trends, and I may be able to visualize one measurement in my head, maybe a few, but as we collect 20, 100, 200 measurements, my head gets swamped and certain structural relationships might be missed. With large data sets, scientists love to plot them on graphs in order to visualize trends, anomalies, and relationships. But how do you plot a three-dimensional data point? A planetarium projects stars in a 3D space onto a hemisphere. And similarly, we can project planes and lines onto a hemisphere and project the intersections to a 2D plot called a stereo net. Let's use our handy spherical teaching tool to explain how these plots are used, and start by describing how planes are plotted. This bowl is what you should be thinking of as your stereo net, or the stereo net is a grid filling this bowl, the lower half of a sphere. We also have this plane to represent the orientation of our planar feature. We place the plane into the bowl and first note that the top linear edge of our plane defines the strike. And we can read that as 090/270. And with a right-hand rule, we say that the strike is 090, 90 degrees. And by the way, it's a good habit to always write the strike direction with 3 digits and the dip with 2, so you don't get confused which is which in your notes later on. And so we write 090 for 90 degrees strike. The dip is 30 degrees, which we could measure with a Brunton, but the hemisphere comes with its own gradations. Vertical at a 90-degree dip, 45-degree dip, and we had our plane at 30-degree dip. And recall that the dip direction is 90 degrees to the right of our strike direction using the right-hand rule. This plane strikes at 090 degrees azimuth, dipping 30 degrees due south at 90 plus 90, or 180 degrees azimuth. And our plane makes a nice curved line across the bottom of the bowl, which is the line we would plot on a stereo net for this plane. So let's take away the bowl and look at the stereo net and see that the curved line needs to be a line that connects the 090 and the 270 azimuth points. Now think that a horizontal plane would intersect the outer great circle, and that represents 0 degrees dip. We count in from the edge 30 degrees, and this arc line represents on a stereo net a plane at 090/30. To do this the old-fashioned way, you place your stereo net grid below a piece of vellum paper or tracing paper. The vellum is just more durable. Put a pin through the center of your grid from below and up through your transparency paper. Perhaps place a small eraser over the pin to avoid injury. And mark your cardinal points on the edges of the grid on the transparency. Then to plot a strike and dip, you note the strike number and find that on the edge of your grid. In our case, we mark the 090 degree point with a tick mark. Rotate the transparency so your strike is lined up with north. So in our case, we rotate 90 degrees counterclockwise to get the tick mark lined up with north. The line intersecting our sphere will have to go to the right of center thanks to the right-hand rule, and so we need to count in from the outer edge 30 degrees. So 0, 10, 20, 30. The arcuate line running up and down the page and going through this point is the line made by a 090 degree striking and a 30 degree dipping plane. Rotate your paper back to its original position so all the cardinal points are lined up again, and you are seeing the plot of a plane at 090/30.
So this curved line means the surface which deep direction is towards the south, and the deep angle is 30 degree, 10, 20, 30, like this.
Or if you will recall, you can go into a program like FieldMove Clino or StereoNet, and all the planes you measure or enter will be automatically plotted on a stereo net for you. Let's try another arbitrary strike and dip and practice plotting it on a stereo net, a blank of which I have posted on the iTunes notes page for you to copy and print off. So let's take a measurement of 01242. Let's start with our physical model. North is the top at 0 degrees, so we count one major grid division clockwise to get to 10, and since each small division is 2 degrees, we will go one small division clockwise to get to 12 degrees strike, and the opposite side will be plus 180 or 192 degrees. With right-hand rule, we know this strike means we are dipping to the east-southeast, and so bring the plane to 42 degrees on the east-southeast side of our hemisphere, and our plotted line for this plane should be so. Now the old-fashioned way, we line up our cardinal points, go to 12 degrees clockwise, and make a tick mark, rotate the transparency so our tick mark is at 0 north, and then find the line on the right side, which is 42 degrees from horizontal, so we start from the edge being 0, 10, 20, 30, 40, and one small division to get to 42. And this arc helps guide our line through this point, and when complete, we can rotate back to line up cardinal points, and we have plotted our 01242 plane. Or we enter that into the StereoNet program and get the same result so much quicker. I mentioned that if your plane is horizontal, then the outer circle is the projection of the plane. 90 degrees dip will make a straight line across the middle of the StereoNet, but the orientation will be determined by the strike. So lower dips will be plotted closer to the edge of the StereoNet and will be more curved, and steeper dip angles will be more towards the center and straighter. We count our dip angle starting at the edge with 0 and increase dip value towards the center of the plot. In a field area, I collect a few and then more and more strike and dip data. As I plot all these on my StereoNet, I might find them all to be about the same or see some shifts between the various formations. But it does start to get a bit messy.
So yeah, if we got many attitudes of betting in the field work like this, and we can clearly see the relationships among them, and got the most tendency, the biggest tendency of them. We can know it very quickly.
So I might clean this up by projecting poles from my planes. Imagine now a line perpendicular to our plane, intersecting the central point of the strike line in our model. It hits the hemisphere at a distinct point instead of a line, and we can plot the poles of planes to clean up our graph. Projecting the pole down puts a point on the opposite side of the StereoNet as the plane projection line, and it is 90 degrees off from the strike line. Now, as I plot many planar data, they more clearly lie as points on my StereoNet, and it might even be easier to see patterns. Points will also appear when we plot any other linear data with dip and dip direction or trend and plunge. I may measure some glacial striations, lines, and embedding surfaces that they are on, planes, and the fault that cuts through this layer, plane, and the slick and slides that fault movement produces, lines. And if patterns are present, they begin to emerge more obviously on the StereoNet. Let's try some common structural forms. Uniformly horizontal, undeformed beds are boring. All bedding planes will just plot as the outer circle of the StereoNet. So let's try tilting all the layers 45 degrees and have them strike at 280. It would be remarkable if every measurement we made was exactly on this average strike and dip, and so multiple measurements will plot like so in planar plots, and as so as poles, where we can more easily see the average value coming through of 280/45. Now let's fold these layers like corrugated cardboard, and if we make measurements, we will get a lot of grouping around here, representing the right limb of the anticlines, and another group around here for the left flank of the anticlines. But the spread in between comes out along the fold axes. With this scenario of folds that are otherwise horizontal, we see that the line of points connecting the flank groups is through the center. But let's try tilting those same layers to be plunging synclines and anticlines. We get the flank groups again, but connecting points starts making arcs off of center. A confusing terrain of hills and valleys and erratic exposure is, over time, boiled down to a plot like this. You may not have seen that you were in a plunging fold while you were out there. Perhaps that you were in a plunge.
So these points, presented by the intersections of the attitude plane.
Down to a plot like this. You may not have seen that you were in a plunging fold while you were out there. Perhaps they were not obvious or not too big. But here's one way you can actually get more information out after leaving the field site. Plot out all your data, and if you see a pattern like this, you know to consider plunging folds with this attitude. There are a few other neat tricks these StereoNets can help us with, but we've covered the basics here. We'll look at some of these more advanced uses of StereoNets when we come back next time, here on Earth Explorations.
Yeah, I realize I need to explain that we usually use the azimuth angle from north, ranging from 0 to 360 degrees for presenting the strike and the dip direction like this. Okay. So this is an outcrop of Mississippi Band Formation in the Rocky Mountains in Alberta, Canada. And this review is looking north, and the rock in the picture is tilted from its original depositional attitude. And the visible plane is the top of a bathing surface. And note that the gravel fields, gravel field stream bed dry at the same at this time of year in winter, and on the lower right side of the image here, and the lower portion of this outcrop is scrubbled clean of organic materials and weathering in each spring season. And the high water mark forms a more or less horizontal line, like this. And in this photo, you may clearly see the high water line. And this man put a length of orange flagging tape across the whole outcrop. And notice that the tape is horizontal and showing a set of points of equal elevation. And this is a strike, and which means the ending line, which joins 2 points of the rock plane, which are at the same elevation on this line. And we now need to measure the bearing of this strike line. And this view is in the opposite direction from previous images. And look at the outcrop sloping towards the stream bed, and the tape marking the strike line, and also the hammer at the top of this slope, just in front of the helper guys. And with these 3 images, you can see the outcrop from different directions, and the left image shows looking right or straight at the rock. And look at the hammer in this photo, and in all the subsequent images, it never moves. Yeah, it could be a a good object of reference. And now we see this image, and several lines have been drawn on the outcrop and with chalk, and all of them are parallel to the original orange tape, flank tape, and they are equally spaced to each other. And these are also strike line. They join points of equal elevation, and we are now creating structural contours, which are just sets of strike lines at some fixed interval of elevation. And some more lines with same intervals were drawn on this outcrop. And to measure the strike, we need to find the contours bearing of or striking of these lines. So to measure this strikes, geological campers can be used. And it is possible to measure the strike with adding campers actually. And Silva Rangers are used in many situations, but note that they work slightly differently from Brownton campers. And the long axis of the campers marked by the two extended sighting arms is aligned with the chalk lines. You see, on the outcrop, and the campers must be held on level. This is shown by the both eyes level in the base on the campers. It can be difficult at first to align the campers with the strikes and hold it level, but this will come more familiarly with practice in the field. Yeah, as stated above, the campers must be held along the strike level horizontally, and the circular bubble here in the base of the campers need to be adjusted to the center position for maintaining this campers on the horizontal level. And you should not only ensure that you are measuring a horizontal line, but that the compass needle can swing freely, ensuring accurate striking. And this is a detail of the previous image of that campus, in which we can see how the bubble is in the red circle. At the white end of the campus, the campus leader points to south. Southwest to south, and so the orientation of the long axis is aligned to bearing 156, and namely or 57, namely the strike is 157. And if we measure opposite direction, the right end of the campus data would point to 337, which is equal 157 plus 180. So there are several standard methods to reporting strikes. We usually use degrees from loss, where the loss is 0 degree. Once the strike has been determined, the dip can be measured after that. Or also you can measure the dip in advance prior to the measurement of the dip strike. And the strike values are now written. We just measure it, and we can write it on the outcrop, and a large white arrow has been drawn perpendicular to the strike lines and pointing down to the slope of the bed. Dip is defined as the maximum slope of the bed which is measured down from the horizontal, and is always perpendicular to the strike. And this is occasionally difficult to visualize. So if you ski, do you like ski? If you ski, dip is easy to remember. When you crash on the steep pitch, the dip is the direction you slide down the hill at the fastest rate, and skiers can call it the fall line. And the other way of remembering dip is noting the 9 water will or would take when poured on the floating bed. And in fact, for beds with no dip angles, this is an easy way to find an average dip over a larger surface. In this image, the helper guys is pouring water on the bed, and it is following the dip. You can see the same direction with this as this white arrow, and the water cannot follow any other path down a smooth slope. Instead, it has to take the steepest line always. So yeah, it has to take the steepest line, and please remember that strike and dip are always perpendicular to each other. So to measure the value of the dip angle, the canvas is, you remember the dip angle? The canvas is placed on its side against the outcrop with a small line level up. The bottom of the canvas has a small level which controls the altitude of the line level and its attached scale. And when the canvas is resting against the horizontal surface, this level and scale give a dip of 0. And when place the canvas on a slope, the level on the back is adjusted until the bubble in the line level is centered. And this image is a close-up of the vernier scale from which the dip angle is determined. And the dip angle is read from the center mark of this scale. The dip angle is read from the innermost scale and is 37 degrees. So the stab of rock is spaced 37 from the horizontal. And in this example can be recorded as either 157 or 337, but the dip is on one direction only. The you can read from here, 37 degree. So the complete strike and dip that has been demonstrated in this set of images could be reported as this. And these are two types of conventions for reporting strike and dip measurements. But for this class, either of them would be correct. And remember that it's not just what you do in the field that counts, it's how you look. Okay. So hopefully, maybe later after you come back to China, we can have some practice in the class or in the field. If it's fortunate to take such good opportunities. Practice class is always important for this subject. So next we need to study the deformation and the displacement of the rocks. So I believe you are very familiar with these terms. You have very good mechanical foundation. Here I will not talk about them in details, just briefly read them. And here you also need to recall that what is elastic deformation, that After it, ductile deformation happened, and at last, eventually, the fractures developed, wherein the material breaks, something like that, in such a relationships between the stress and strain. Okay. And if we squash a homogeneous rock in laboratory and make the confining stress high enough with hydraulic ram, it will highly fracture. And two sets of fractures often developed, and they are called conjugment jacket faults. They will be formed after the fractures develop. So, due to Andersonian theory, the three different kinds of faults will occur due to the various dominant stress. And faults are fractures that have had displacement of the rock along them, including normal faults, thrust faults, and strike slip faults. So the brittle failure is referred to the permanent deformation of the rock by fractures, and the ductile failure demonstrates the deformation without fractures by bending or flow, like this. And the two types of brittle deformation could be classified. One is joints, and the other one is faults. The joints illustrate the fracture with no movement of rocks of either side relative to each other. And the faults are referred to the fractures where the opposite side have moved past each other. So the biggest difference between them is that the displacement joints has no displacement aside the two sides, and the faults must produce the displacement between the two sides of the structure. So such kind of joints are not formed by stress, but are formed by the flow of magma. You remember magma? When it erupted from underground, under gravity, it usually occurred in the typical igneous rock, the basalt. Yeah, if you see some such vertical joints in the field, it's most likely to be the basalt, very typical rock type of igneous rock. And it can be very well developed. I got a very great impression of such cooling joints in the Hebei Mountain in Sichuan during the field practice in my undergraduate course. And hopefully we also have this chance to touch them in nature and see it by ourselves. And this outcrop is in the America, California. And limestone, which is a rock type of sedimentary rock. The basalt is igneous rock. The limestone is composed of calcium carbonate, and which can be easily dissolved on the Earth's surface in nature by the surface water or rainfall. And the block joints like this in limestone enlarged when mildly acidic rainwater causes solution weathering, and which belongs to the chemical weathering. Yeah. Okay. Like I said, the faults are the fractures with the displacement between the two sides of the fault. And shear fractures are formed where the rocks on either side of the fracture have moved relative to each other. Yeah, it's different from the joint. And faults commonly create zones of badly broken ground, and that are weaker and less stable than adjacent rock, with implications for foundation bearing capacity, slope stability, and tunnel roof integrity. So if we design a tunnel or bridge on the hill slope or the relevant constructions, we need to pay attention to the faults and the nearby rocks. They might be a very fragment and disintegrity. And we also use dip and strike to describe the orientation of fault, like we do in the for the bedding plan. Yeah, strike is the direction of horizontal line on a surface, and dip is referred to the angle that the surface dips. And due to the moving direction, the fault classification includes strike slip fault, deep slip fault, and oblique slip. And the upper block is named the upper block of the fault is named hanging wall, while the lower block we call it footwall. Yeah, I'm sure this can be easily understood for you. Yeah, and if the two blocks aside the faults displays, if its displacement is along the AB line, it's called net slip, which is parallel to slip vector. And if a fault displaces along AC or BD, we call it a strike slip, which moves parallel to the strike. And AC and BD is the amount. Yeah, the length of the AC and BD is the amount of the offset measured in the fault plane parallel to the strike. And if a fault displaces along CB or AD, we call it dip slip, which moves parallel to the dip. And the length of them are the amounts of offset measured in the fault plane parallel to the dip. Yeah, as I said, the normal fault is the fault along an inclined plane in which the upper side of hanging wall moved downward with respect to the lower side of footwall. It's opposed to the reverse fault. It has another name of extension fault. And such kind of fault often dips at greater than 45 degrees. And oppositely, reverse fault is a fault in which the rock above the fault, the hanging wall, is displaced upward relative to the footwall, which is the rock below the fault plane. And if the dip angle is less than 30 degrees, we often call it thrust fault. And it commonly dip less than 45 degree. And they also have some other name, thrust fault and contraction fault. And strike slip fault is a fault on which the movement is along the strike of the fault horizontally. And how can we identify it is a left or right lateral fault? It's very simple. If we, for example, for this fault, if we stand here and look it from the right side, the father block move to the right is right lateral, and if the father block move to the move to the left relatively, it's left lateral fault. And faults also generate some striation on the outcrop, and it's called striation or stickerside on the fault surface, which is a strong evidence for identifying fault. It's formed for the friction between the hanging wall and footwall, and which is in the Europe, Greece. And this is another taking the direction of this the photograph. Yeah, like I said, when the dip angle of reverse fault is less than 30 degrees, we often call it a thrust fault, like this. And it commonly slide along the some weak layers on flat portion and cut off of the section in the ramp portion. So we can imagine previously the rock strata is lying horizontal, and after some compression stress generally in this region is the layer will be climb up and cut up the section of this rock and might produce the fault, like thrust fault like this. And in nature, especially in actively tectonic mountainous areas, the fault orientation could be very complicated, like this, such as the duplex in the thrust belts in Alps in Europe, Himalaya in Asia, and Rockies in North America. This is a field outgrowth of duplex faults, and which are formed within thrust faults and generate a pile or stank of thrust sheets. This is a Normanshine fault, which is to the west side of Chengdu. It's a typical thrust fault built in the western strand between the Strabasin and Tibet Plateau. And the middle one of these faults created the biggest earthquakes in this century, the Wenchuan earthquake. Another famous fault built, the St. Andreas fault, is about 1,300 kilometer long, and it has existed for over 20 million years. It caused streams, you can see, offset with strike slip of about 100 meters in a very recent displacement. So the stream, usually is continuous with this, but after this strike slip fault, the displacement could be attaining 100 meter, and which means the original stream should be continuous here, and it becomes what we see today. So next we need after the brittle deformation or fault, we need to explain the ductile fault deformation. During the mountain building or compressional stress, rock may deform plastically to produce faults, and generally a series of faults is produced, much as a carpet might wrinkle when you push on the one end. A tectonic fault is a typical geological phenomenon formed during the mountain building, like in Himalaya and the Nordmanshire Fault. The ductile deformation is a permanent distortion of material without fractures, and this is the biggest difference from a fault. And the three basic effects were proposed. For the sphere in the three-dimensional model, it can transform to an ellipsoid by compression horizontally, and if the deformation develops on a layer, it will be folded like this, and the fabric of structures will also change to some alignment pattern or of minerals by rotation, recrystallization, or both with the compression stress. And faults commonly developed in the shortening of the rock layers, like this. So finally, we could commonly see such faults in the rock outcrops in nature. So how can we describe this such a geologic structure? Firstly, the faults with an upward curve is attributed to this upward curve is attributed to anticline, like this, while the faults with a downward curve is referred to syncline, and the enveloping surface will control the amplitude of the wave-like fault, and the wavelengths you must be already very familiar with. And hinge line joins all the points of equal curvature on the fault surface. And for example, the hinge line of the faults in the lower right photos should be like this. And the hinge line could be horizontal, and it could be also inclined. And this is a non-plunging anticline with a horizontal hinge line. And this is a plunging anticline with inclined hinge line, which has a deep angle with the compared to the horizontal surface. And from this right photograph, I think you can identify which type the fault is, anticline or syncline. Obviously it's anticline like this, but it has plunging angle of hinged die. And it's simple to see the plunge direction is towards the loss. And if you can imagine a horizontal surface cut this anticline, you will easily understand how such a plunging fold is like in this underground. Okay, next I can tell you some examples. We studied in my previous research, and this is a geology map we made in the dish area. This is the Shimon slide. The Shimon slide. Yeah, I talked in last week, and we identified at least 2012 landslides in these areas, and note that in this section, all of the large landslides were located on the left back of the major river. So here I like to talk about several of them to present the most typical landslides characterized the geologic structures in the domain. And let me start from the Maladin landslide. And in this landslide, and the major rock type here is alternating beds of sandstone and shale, shown as green color in this figure. And the red color indicates the landslide deposit, and the yellow represents the talus, which is a deposition from the rockfall from the cliff. And we chose because the scarp is not easy to reach, so we chose the outcrop on the opposite back to reveal the geologic structure features to deduct the structural condition here. If they, by the way, if we saw the head scarp of this landslide by via a telescope, we could see it. We could see some tight folding on it, and also when we observe the opposite side outcrop, tight folds you can see, and joints with in red line were also investigated. And in stereolite analysis, it's you can know from the videos I played just now. The pole vector shows the beddings and the joints along the northeast to southwest, and the contours of the structural intersections suggest the axis which dips 10 degrees towards the WSW. It means southwest to the west. And please note that these points from this large numbers of the structural planners. These are the intersections of them, and it could be when we made the contours of these intersections points. We can see the biggest tendency is around here, which could represent the plunging direction of all this structure. So this the structures, the general plunging direction of the structures is towards the WSW. And when we move to the northward to the Dragon Andesite, the outcrop mainly consists of marble shown as blue, and the bedding on the scarp generally exhibits as a syncline like this, and some drag folds could be seen. And from natural, we found remarkable lineation, which could suggest the direction of hinge line. So yeah, by the comparison of stereonet of lineation and bedding intersection, the concentrations of the sites are consistent, and it's also demonstrates the plunging direction of all the structures is towards west. So similar, these two andesites are very similar. They have the folding plunging direction to the west, and thus we can therefore we can understand the folding plunging direction could highly correspond to the sliding directions of dragons and Dragon andesite and Maladin andesite. So yeah, this schematic shows the movement. We can see easily see along this direction in this rock stratum is not easy to slide. And however, due to the plunging angle of the fold, even it is very gentle, and the rock slide could be happen much easier along the plunging direction with some high angle joints. And this can intensely prove that these two andesites were controlled by the plunging direction, plunging condition of structures. And the Zagros Mountains make up Iran's Iran's largest mountain range, and they have a total length of 1,500 kilometers from western Iran. The Zagros Mountains were formed by collision of two tectonic planes, the Eurasian and the Arabian plates, and the stress induced in the Earth's crust by the collision caused a extensive fold of pre-existing layered sediment rocks. And subsequent erosion removed softer rocks such as mudstone and siltstone, while leaving harder rocks such as limestone and dolomite. This differential erosion formed the linear ridge of the Zagros Mountains, and the depositional environment and the tectonic history of the rocks were conducive to the formation and tramping of petroleum. And the Zagros region is an important part of Persian Gulf oil production in the Middle Asia. And the fold axial surface represents the axial surface joins all the hinge line together. You can see it in this figure. And this is outcrop of sedimentary rock. Okay, this is some the bed plan of the sedimentary rock, which has been folded by some tectonic activities. We can recognize from the developed bedding plans. And if you take the photos, the field like this, never forget putting a scale within the scope, and the hammer is really the best choice. So the folding axial surface in this outcrop is approximately like this. You can see on this one. Okay, next let's move to the class and the forms. And some scholars discriminate class and forms for the folds, and the forms is usually used for the description of the folding form and shape, and class is usually used for the description of the exposed condition we can observe in nature. But yeah, they are very similar, and either of them can be used for the description. And for example, in the beginning of the layer of sedimentary rock should be deposited horizontally, right? And then the layer are folded by some compressional stress. And after that, our surface are eroded by water, wind, or some other dynamic factors. So we can observe it from the surface, like this. And due to the gravity, the deposition process should be always from lower portions to the upper portions. So the older rocks generally lie below the young rocks and are only exposed by erosion. And these 5 layers, A, B, C, D, are in order of their age that are formed from old to young. So when we saw outcrop with some anticline or syncline in the field, how can we recognize its anticline or syncline? So one way is that when we just walk along this direction, perpendicular to the beam, perpendicular to the hinge direction. If we found the middle rock is the oldest one, we can like this portion. We can identify it as an anticline. And if we found the middle portion, the rock type is the youngest one in the fold, we can recognize it as a syncline, like this. And one more classification due to the pattern has been made for the shape of the fold. So as the name suggests, symmetrical and asymmetrical folds have symmetrical and asymmetrical curves respectively. And the overturned fold has 2 folds with the same deep direction. So if we saw this without the top portion of this fold, we just walk like this. If we could find some repeated rocks, if we walk here. So we need to remember that if the middle rock is the oldest one, it can be sure to identify it as such a anticline of the fold. Okay, and the recumbent fold is referred to the fold with nearly horizontal fold axis surface. Okay, this and some other another fold classification. And this is a very funny phenomenon we found in the field along the Minjiang River in my study area of Sichuan, in my doctor course. And this recumbent fold seemed like a flying dragon and some local people burns joystick to worship it as a dragon god for business or harvest, I guess. So just now I introduced the dragon nestite, which is nearby here. Yeah, it's named by such a very interesting phenomenon. As for the fold attitude, we usually use actual surface to describe the attitude. And you can see the upright fold develop with a vertical axis surface in the right image. The recumbent folds are formed with a horizontal axial surface in the lower left image. And while the inclined folds between them have an inclined axis surface in the lower right image. This is easy to understand. And as to tight extent, the tight degree of the fold tightness are divided into gentle, open, close, tight, isocline fold according to the decreasing interleave and interleave angle. Like the arrangement is like this. And the folds I talked just now are typical tight folds in the activity tectonic region, which is usually located in the mountainous region. And these folds are classified by angular extent. The most angular folds, we call it Jevro folds. And when the the least angular is continuous curve, and the intermediate one is the rounded hinges and straight with straight limbs. And speaking of the symmetry of the folds, symmetric fold have limbs with relatively equal lengths, whereas asymmetric fold have a long and short fold limb. And this has been already introduced just now. And the small folds in small scale also developed in a big general fold. And for example, this is an anticline fold in generally, and associated with many angulate tiny folds within it. This photo also typically shows such a structural phenomenon. General anticline with many angulate tiny folds. And additional features are generally defined as a segmenting set of features that are overlapping or have a staggered arrangement. The inlation tension fractures may indicate the direction of the displacement. I'm not sure what this term originated from. It means the arrangement or order of elation. And sometimes we can see such a phenomenon with the S-shaped tension gashes filled by chords like this. And they are generally S or Z shape depending on the sense of the shear along the dome. And this type of actually it's made by extensional stress. So this type of extensional fracture is really a mineral field and form an initial areas along the shear zone. And dome, as we know, dome is a vault in the form of a portion of a sphere like this. It will be easier to form in an open echinidal fold with oldest formation imposed in center and the youngest formation in surrounding portions. Yeah, it's a broad open echinidal fold on a regional scale. It's really a basement dome. And on the other hand, a synclinal fold facilitates the formation of a basin of the youngest formation in center and the oldest formation exposed in surrounding portion on the surface. But note that this basin is in a small scale compared to Sichuan Basin. It's not the formation of a Sichuan Basin. Formation of the Sichuan Basin is some other mechanism. In a more much larger scale tectonic activities. Okay, next I will talk about another essential point, the conformity in rock stratum. It just demonstrates the relation of adjacent beds not separated by a sedimentary discontinuity. Conformity. Yeah, the unconformity is a plan to break between the two sequences of rocks with different dips. It indicates a period of Earth movement and tectonic deformation between the times of sediment deposition. It forms a major structural break. The older rock must be more lixified and folded, and perhaps more metamorphosed than the younger upper rocks above unconformity. And therefore, the uplifting and the erosion play a significant role in the great impact on conformity. So the point is that the deposition of the rock formation is originally horizontal, and after that it could be influenced by the tectonic and the erosion, and after that a new period of the horizontally deposition happened, so such unconformity formed and last. So what is uplift? A structurally high area in the crust produced by positive movements that raise or upthrust the rocks, as in a dome or arc. And in engineering, uplift is that any force that tends to raise an engineering structure and its foundation relative to its surroundings. It may be caused by pressure or of subjacent ground, surface water, expansive soil under the base of the structure, or natural force. And some movements due to unloading, isostatic change, compression shown by marine deposits and fossils now found on the mountain top. Okay, the subsidence is the perversity term to the uplift. The sudden sinking, it is referred to the sudden sinking or gradual downward setting of the Earth's surface with little or no horizontal motion. The movement is not restricted to in rate, magnitude, or area involved. And subsidence may be caused by natural geological processes, and such as solution, thawing, compaction, snow crust warping, or withdrawal of fluid, lava from beneath solid crust, or by mass activity. A sinking or down warping of a large part of the Earth's crust relative to its surrounding parts, such as the formation of Rift Valley or the lowering of cold due to tectonic movement. And this schematic illustrates the unconformity between the parallel strata. The unconformity occurs in sedimentary rock at which strata are parallel, and the contact is a simple building plan. And for instance, the sandstone, sandstone originally overlies on limestone under the water level. Then uplift happen, and the erosion starts and removes the layer of sandstone. So the sandstone layer disappeared in this figure, and after that, the further deposition of sedimentary rock begins, and the new rock layer of shale is formed and overlying on the older limestone, and then uplifting occurs again. Finally, the rock stratum is short of the layer of sandstone, so there's no sandstone. Eventually we observe this outcrop, which should have been interpreted between the old limestone and the young shale. And this is what we can observe, the unconformity on some outcrop of this rock stratum. And angular unconformity is kind of interesting phenomenon we can observe in the field without fault in it. In the lower right image, we can see the horizontal orientations of the lower rocks are inconsistent with the upper portion. As we know, the steep of a fault could cause such a disconformity too, but there is no fault between them. The angular unconformity is the unconformity in which the older stratum dip at a different angle than the from the younger stratum. So the forming process of angular conformity is similar to the process on the previous slide. So the difference is that before the second deposition of the lower portion of rock layers suffer tilting process, which lead to inclined layers, and the later deposition of the upper portions are formed horizontally. So finally, such an angular unconformity are produced by the uplifting, tilting, and erosion, and the final deposition again. So such a unconformity in which the older stratum dip at a different angle are formed. And so putting it another way, and first the sediments deposited maybe beneath, and secondly the folding and deformation start up during the mountain building that exposes the rock to erosion, and thirdly the surface is eroded to an uneven plane. At last, subsidence happens below the sea level, and the younger deposited on the former erosion surface. So this is an angular unconformity. Okay, the one more type is the non-conformity. non-conformity to be done to the one of the unconformity types. It is a unconformity type, unconformity where the older rocks are Pluton origin. You remember Pluton? Plutonic origin. Plutonic rock is a kind of igneous rock, right? The point is that the younger deposition of rocks deposited on the igneous rock formed by intrusion of magma. Okay, some further terminology need to be introduced here. At first, the escarpment. It is a ridge which is formed by hard beds overlying a softer with a small to moderate dip, has one topographic slope steeper than the other. For example, the dolostone is much harder than the shale, and if any surface or erosion happened, the dolostone is hard, which is more stable to maintain the shape of this cliff, but the shell is softer. When it is eroded, it's not easy to maintain the shape, so it's always keep. It's relatively keep gentler slope surface. It is an asymmetrical hill or dipping beds of strong rock exposed by differential erosion of weaker rocks above and below. In other words, if we observe the rock from the air, we can see the young rocks. In other words, we can, if we see this from there, we can easily see the cliff in the hard rock above the soft rock. Okay, and the outlier illustrate an outcrop of rock which is completely surrounded in plain by other older rock is called outlier rocks. And so put it another way, if we observe this rock from the air, we can see the young rocks surrounded by old rocks, and this is usually due to either an eroded syncline or in a hill. And the inlier is an outcrop of old rocks surrounded by outcrops of younger rocks, and its presence on a map indicate either an eroded anticline or a valley. And you should notice that in terminology, tectonic and structural geology are quite similar, right? So after the introduction of this chapter, we can see they both describe the deformation of Earth, but we usually use tectonics as a term about the deformation of extensive areas such as plate movement, which I will talk in our next class. And whereas structural geology is referred to a more local deformation in rocks or thick layers. So in summary, the tectonics and the structural geology, they both describe the Earth's deformation, but the scale, the description scale, scales are different. Tectonics is bigger, and the structural geology scale is smaller. Okay, this is the part of today's class. So yeah, next class I will take some discussion about the tectonic and the plate tectonic and some knowledge about the plate drift scenery. Okay, guys, see you tomorrow.
Hey guys, this is the